mixed species, then that cusp is known as oscal inflection. Point of oscal inflection. I'll talk about that. What is that? If there are mixed variety of both these species are mixed together. Okay, if I take, there is a suppose tangent here, this is a cusp we are talking about. Now if first cusp is, okay, now in this case, this is first, second species, beak-like cusp. Okay, and here it is second and first. This is first species, horn-like cusp, and this is beak-like cusp. Both are mixed together. Both varieties of cusp are mixed together. This is known as point of inflection, but this is known as oscal inflection point. Point of oscal inflection. Point of this double point is known as point of oscal inflection. This we will talk about inflection, point of inflection, in the next lecture series, 78th one. But up to now we have talked about what are the different kind of cusp, node, and this point of oscal inflection, because this includes both these species. Second species, or beak-like cusp. This is horn-like cusp. Both are mixed together. Now this is second curve. This is the first curve here. This is the tangent line, T and T dash point. Let me take this is P point here. P point is double point, but here we have mixed the two species, beak-like cusp and horn-like cusp. When both species are mixed together, this is known as oscal inflection. Oscal, where CUL, oscal inflection, point of oscal inflection. Okay, so this inflection point we will talk in the next lecture series, but at the moment we have to talk about these questions now. Okay, now the process of finding the tangents, which I have already described, that we always find out the given equation. We consider that equation, how to find out double point. To find the double point, how to find out double point, let me talk about to find the double points. First we have to find out, the double points. What we do, what the process of finding the double point, conditions or necessities of this. What are the conditions for this? To find the double point on a curve, so what we do, first of all, we find out the equation of the curve equal to that fxy equal to that linear rational algebraic function. Okay, if there is a rational algebraic function given, that is a curve, equation of the curve. Let me take any curve. All these curves are rational algebraic functions. All these rational algebraic functions are first considered as this fxy equal to 0. Then we find out del f, del x is 0, we will equal to 0. Del f, del y, we will differentiate partially with respect to y, with respect to x. Then we will equal them to 0. We will find out the points here. If the double points are satisfying the equation of the curve given, then we say that that point is a double point. Actually, that point is double point. Now, upon that double point, we will find out double derivative del square f upon del x square. Okay, and at that point, what is, suppose that hk point is there. Hk is a double point we have calculated. That point we will find out. At that point, we will find out what is del square f upon del x square. What is this value? We will find out. Okay, and that numerical value is calculated. Del square f upon del y square also we will calculate from this equation. Del square f upon del y, del f upon del y, and then we will differentiate it again with respect to y. We will calculate del square f upon del y square, del square f upon del x square from this one. Okay, we will solve these two values on this point hk given. Again, hk point, whatever value comes out, and then del square f upon del x del y also. This function del f del y, we will differentiate it with respect to x. We will get del square f upon del x del y. If whatever this value comes out, okay, then we will just check whether tangents are coincident, tangents are distinct, or tangents are imaginary. So what we have to prove then? Just to check the double point. What kind of double point is that? If that double point is representing a cusp or a node or imaginary point or conjugate point, I mean isolated point or conjugate point, then you will find out the tangents, tangents upon that point, double point. What are tangents? Type of tangents. So tangents will be coincident, or distinct, coincident, or imaginary. Then what is the condition of that? We have to prove that del square f upon del x square, del x del by, del x del by whole square of this minus sign. This is del square f upon del x square into del square f upon del y square. The difference of these two, b square minus 4ac, 4 will cancel out because here it was 4 also, here also 4 will cancel out, is greater than or equal to or less than 0. What does it mean? Either this value is greater than this, or we can say, let me write here, or if del square f upon del x del y whole square is greater than del square f upon del x square, del square f upon del y square. If this value is greater than this, then node will lie. Tangents are distinct. In this case, tangents are distinct. Tangents will be there. Distinct tangents or real tangents will be there. Tangents are distinct, or in this case, curves are real. Undoubtedly, tangents are distinct. That this condition will show that tangents are distinct. That means node will be there. There will be a node. There will double point will be a node. Node condition for node is that tangents are distinct. This is the condition here. We will find out this del square f upon del square del x del y whole square is greater than this multiplication of these two at the given point. Then that double point will be known as a node. And to find out this equation of the tangents, we have to equate the smallest degree term in the given curve to 0. Whatever the equation after shifting the given double point to whatever the double point we have found out, the shifting the origin to that point, we solve that equation. Then we will equate the smallest degree term, at least square term of the given equation to 0, because only then the two values of the function given, x variable or y variable, will lie. So at least a square degree must be there. The degree must be 2. At least 2 degree or degree 2 must be there to equal to 0. So we have to equate the smallest degree term or terms to 0. From there we will find out what the equation of values of the tangents and equation of the tangents. And if from those tangents we will find out then what the value of y or x. If the value of y when x is small, positive n is small, x is negative n is small. And what is the value of y? Is it double value negative and positive? If they are double value, then cusp will lie on the positive side of y, or on one side of the y. So this is how cusp will be there of first species. Cusp of first species will lie. And if the values are same, then the cusp will be there. And if the value is, this distinct value is negative, is imaginary, not possible, then we will say that tangents are not real. So then conjugate will lie. The point will be a conjugate point or isolated point. So then no need of finding out the tangent then. But only in case of cusp we have to shift the origin to the point given. At that point we have to find out what the value of. We will consider that point equal to p, and then we solve the value of p. This is the process of finding the double point on a curve. Let me find out the nature of the curve, nature of the double point, what is given to us. Now let me solve the questions. The process I have talked about. In case of finding the equation of the tangent, we will equate the smallest degree term of the given equation 0. From there we will find out equation of the tangent, okay, by equating to 0. Now let me take the questions one by one. Now this is the basics of this whole topic, which I described in the 76th lecture also. But in 77th, I have taken some more questions of a similar type, but these questions are of difficult level, okay, or different level, I mean, more difficult one, because the students have asked me these questions again. They have given me more questions also, but it's not possible that I have to repeat the same lecture again and again, or more questions I have to take of the same topic. Okay, so these questions I have taken from the previous question onwards. This is further discussion upon node, cusp, and conjugate points. Further discussion we may say, or this is some more points on the same topic, similar points. This is double points we are talking about. Now question number 1, let me solve. For the question number 1, they say determine the position and character of the double point. Okay, double points on this curve given. So we have to find out the position and character of the double point. Character means here the double point is the cusp or a node, but the position of this, okay, it is lying, okay, in the positive direction of the y-axis, or one side of the y-axis or other side of the y-axis, or whatever. This is position of the double point. So determine the character and position of the double point on the curve. So let me take the curve here. Let fx by the given curve here is y into y minus 6 minus x square into x minus 2 whole cube equal to 0. This we have taken as fx by, as we always consider this function, that equation of the curve given as fx by. Now this equation we will differentiate with respect to s just to find out double point. To find out the double point, existence of double point on a given curve, what we do, we consider that function as a fx by function or function of x and y here. We take it as fx by. Okay, then we will differentiate it with respect to x. Differentiating it partially with respect to x and y respectively. So what we get here, del f del x is equal to how much? Let me know. This is by term, so it's 0, because in case of partial differentiation, if the variable is different other from with which we are differentiating, with respect to which we are differentiating, the variable is other than that will be 0. So this is 0. Differentiation of this, but these are two terms here by product rule. So this product rule is, first let me differentiate x square. This is twice x only. X minus 2 whole cube as it is. Then minus sign x square now as it is. This 3 will come before. We have to differentiate the second term. Let me write clearly. This is minus 3x square into x minus 2 whole square now left over. Okay, because now this is differentiated again, so x is 1, so multiply by 1 is this only. Okay, so this is the second term. But before, okay, equating it 0, this and this, sorry, now differentiating this with respect to y and y, del f del y is equal to how much? This equation, this term will be differentiated only by product rule again. Y is by 1, that means y minus 6 as it is. Then plus sign, now y as it is into 1, because this is y differentiated as 1. This is 1. First, this y is differentiated, then second function y minus 6 as it is. Y is 1 differentiated with respect to y. Then y minus, okay, 6 is to be differentiated. Y taken as it is. So y is 1 here, 6 is 0. Only y into 1, that means this. Okay, so this is second differentiation. Again, differentiating it. Again, differentiating these, we get, what do we get here? This is del square f upon del x square. Let me differentiate these two. Differentiation of these two I mean, this again multiplication, law of multiplication. So first x is differentiated. X is 1, x minus 2 whole cube as it is. There's minus sign here. Then minus sign twice x as it is. This 3, this is to be differentiated. It will be minus 6x into x minus 2 whole square now. This is differentiated. Minus x square is differentiated. This is minus 6x only x minus 2 whole square as it is. Again minus 2, 3 is 6, minus 6x square now. This is x minus 2 only. Why? Because now x minus 2 whole square is differentiated. This will be twice into x minus 2. So 2 into 3 is 6. 6x square as it is. This is x minus 2 now left over. Only one problem. Okay, so if I solve it, let me further solve it. It will be x minus 2 similar terms. Okay, these two are like terms, I think. Same, so it is 12. This is x square. Okay, so this is minus 2 into x minus 2 whole cube. The first term, this one. Then minus 12x, this and this, into x minus 2 whole square, minus 6x square into x minus 2. Okay, this is del square f upon del x square. Now, del square f upon del y square, del square f upon del y square, differentiating this equation. Let me take this is the first one, this is the second one, or this is the first one. Let me take this is second one, this is third one. Now this is the fourth one. This is the fifth one we have to take. Del square f upon del y square. This is to be differentiated. This is 1 plus 1. That means 2 only. This is twice y minus 6. Twice y differentiated is 2, so only 2. Del square f upon del y square. Now del square f upon del x del y means this third equation is to be differentiated with respect to x. We got here 0 because nothing there, so this is 0. Now let us equate del f del x equal to 0 and del f del y equal to 0 just to find out values of x and y. The point double point. So to find out double point, what we do here, let me write it here. So to find the double point, we equate del f del y, del x equal to 0 and del f del y equal to 0. So what we get? These two equal to 0. This first one, if I write, then this is minus twice x into x minus 2 whole cube minus 3x square into x minus 2 whole square equal to 0. If I take common, let me take minus x, okay, into x minus 2 whole square common. What is left over? This is 2 into x minus 2 only. This is x minus 2 whole square and x I have taken common. This is minus 2. So this is plus 2 only, minus x also I have taken common. This is plus 2 into x minus 2 only. Then minus 3. This is plus 3 into x. Why? Because x minus 2 whole square I have taken common. So this is equal to 0. What do we get? Okay, so this is 2x plus 3x minus 5x. Okay, that will again write. This is minus x into x minus 2 whole square. Within bracket it will be 3x plus 2x 5x minus 4 2 to the 4 equal to 0. This implies that x equal to 0, x equal to 2 from this one, and x equal to 4 by 5. Okay, these are the three values of x: 0, 2, and 4 by 5. Okay, after solving del f del by 0. Now del f on del by equal to 0, this one 0, so 2 by, and del f del by equal to 0 imply that this is twice y minus 6 equal to 0, or y equal to 3 here. What are the points? Y is 3 only and x are 3 values. What are those 3 points? Let me write here. So those 3 points are x is 0, y is 3, x is 2, y is 3 only, x is 4 by 5, and y is 3. We have 3 points, 3 double points maybe, and out of them which are possible double points. Let me find out the actual double points here. What are those actual double points? Let me check. So if we put these values in the given equation of the curve, if this equation is satisfied, then that particular double point, or all may be there, all double points may be possible, but we have to check those 2 points, these 3 points here, after substituting the values, okay, in this equation. Let me check these 2 values. So if I substitute x equal to 0, 3, 0, 3, satisfying this equation, where the equation was y into, given equation was y into y minus 6 equal to, it was x square into x minus 2 whole cube, whole cube minus 9. That was the given equation here. Okay, so y into y minus 6, it was equal to x square into x minus 2 whole cube minus 9. The equation given there. So let me take whether left hand side equal to right hand side at these points. The first point is 0, 3. X is 0, 0, 0. This is 0 minus 9 in the right hand side only. If I substitute x here in the right hand side, we get minus 9. The left hand side, if I put 3 in place of y, so y is 3 into 3 minus 6 means minus 3. Minus 3, 3 and 9. This is also minus 9. It means 0, 3, the first point is possible. So this is satisfying the given equation. So 0, 3 is the possible double point. Let me check others also. It's possible double point. One of the possible double points is 0, 3. Let me talk about 2, 3. 2, 3, if I put here 3y and 2 here, this is 0 again because 2 minus 2, 0. X is 2 here. The second point is 2, 3. So at 2, 3, if I put here 2 minus 2, 0. At x equal to 2, this term is 0, only minus 9 is left. In this case, 3 minus 9, so this is also possible. So 2 and 3 is also satisfying, is also a double point. Is a double point possible? This is also possible double point. Now at point 4 by 5 and 3, at 3 left hand side is minus 9 undoubtedly. If I put here 4 by 3, now this value will come out something, and this is minus 9, so this is not possible because it is not satisfying the given equation of the curve. So third point is not possible, is not a double point, possible double point, because it is not satisfying the given curve. Equation of the curve is not satisfied by the third point. Only 0, 3 and 2, 3, these 2 points are double point possible. Now let me check what is the quality of these points, whether characteristics of the position and character of the double point. Now this double point are cusp, representing a cusp or a node or a conjugate point. That let me check. For that we have to find out the value of del square f1 del x square. Okay, del square f1 del x square, which is this one. Del square f1 del x square. This is del square f upon del y square is 2 only. Okay, del x upon del square f1 del x square. This is the value. Okay. Now at first point 0, 3. Okay. At 0, 3, x is 0 here because y is not there, so x is only 0. We have to substitute This is only possible value. This is 0 because x into something 0. This is also 0. These two terms are 0. Only the first term will give us minus 2 whole cube means 8. 8 to the 16. So minus 8 and minus 2 minus plus 16. Del square f upon del x square at the point 0, 3 is equal to 16. What the point? Now, in case of del square f on del y square, because there is numerical value only, and del square f upon del y square is there 2 only, because even if we substitute the value 0, 3 or not, this is 2 only because this is only numerical value. This is 2 only, and this is 0. What do we get? Del square f upon del x del y whole square is 0. And these two are 32 value, multiplication of these two. This value is greater than 0. That means imaginary point. 0, 3 is a conjugate point. Okay, because here tangents are imaginary. Tangents are not possible. Okay, so at the point, okay, at 0, 3, the double point, the tangents are imaginary. Tangents are imaginary. Tangents are imaginary. Why? Not possible, you may say. As del square f upon del x del y whole square is less than del f upon del x square into del f upon del square f upon del y square. Why? Because this is 2 into 16. This is 0 here. Del square f upon del x del y is 0. This is 32. 0 is less than 32, which is imaginary because right hand side is greater than this one. So this is imaginary point. No distinct points are there. It is not a possible double point because at this point conjugate points are lying. This will represent a conjugate point. Okay, so this 0, 3 point is a conjugate point. Okay, so it's a conjugate point, not a double point. We cannot say it's a cusp or but it's a conjugate point. Tangents are imaginary. Then we cannot say that this is a conjugate point here. Now let me talk about 2, 3 point. At 2, 3, at 2 and 3 means second point. So at the first point there is a conjugate point. First double point is a conjugate point here. At 2, 3, this is also possible double point. So at this 2, 3, let me find out what del square f upon del x square. This is 2, 3. This is 0 at 2 point. This is also 0. This is also 0. Okay, 0. Del square f upon del x square at the point 2, 3 equal to 0. Why? Because x minus 2, 0, x minus 2 minus 2, 0. X is 2 here. So this is also 0. This is also 0. Every term is 0. This means 0. What is del square f upon del y square, which is 2 only? There is no difference, only 2. And this del square, so both are equal. It means del square f upon del x del y whole square is equal to, in this case, del square f upon del x square into del square f upon del y square. Why 0 equal to 0? 2 into 0 is 0. In the right hand side, 2 into 0. This is 0 into 2. This is 0. The left hand side is already 0. In 0 equal to 0. This means there will be a cusp. Tangents are distinct here. Sorry. Tangents are coincident. Here tangents are coincident. What does it mean? It means cusp will lie. What kind of cusp will be this? That let me check. So what we do here, for that we have to put the we have to shift the origin to this point 2, 3. So at 2, 3, from this it is clear that at 2, 3, the double point 2, 3, second point, coincidence, tangents are coincident, so cusp will lie. First thing, at 2, 3, the double point, tangents are coincident, coincident. Why they are equal? Coincident. So a cusp will lie. So tangent point, this double point will be a cusp. So it will be a cusp. So a cusp will be there. Cusp will be there, or this double point will be a cusp. Okay. Now what kind of cusp? What nature of cusp? What do we do? Shifting the origin to the point, to the double point 2, 3. The double point 2, 3 is to be considered as the origin. For that we have to change this. Therefore, the equation of this curve will be y plus 3. In place of y, we substitute y plus 3. The second bracket is y plus 3 minus 6 is equal to x square. That means x plus 2 whole square. Second point is x plus 2 minus 2 whole cube. Okay, so what do we get here? This is y plus 3, this is y minus 3. This is nothing but y square minus 9. Y square minus 9. Here it is x plus 2, minus 9. Minus 9 is also there, I'm sorry. This is minus 9 here. I'm sorry. So here it is minus 9 also. I'm sorry. I just, didn't write here that minus 9 is also there. It is minus 9 point. So minus 9 in the end will be there. So this is y plus 2. We have put down whole square. This is 2 to cancel out. So x cube only minus 9. Okay, so this is that equation. Now equating. Now this minus 9 and minus 9 cancel out. What do we get? This is y square equal to x plus 2 whole square into x cube. Or here y is equal to, or if I equate these, y square equal to 0, y equal to 0, y equal to coincident points are there, there is no doubt about that. Y equal to plus minus, this is x raised to 3 by 2 into x plus 2. X plus 2. So for smaller values of x, if I take x smaller values of x, here, if I substitute, y will be, because positive, this is plus value, for small value of x, y will be positive and negative both. For smaller positive value of